chaos theory is even weirder than quantum theory. Previously, it was shown how the gap between the classical world and the quantum world is very small in some places, theoretically such that very small change to the theory, such as switching to complex time, can be all that's needed to switch to working in a quantum representation. Chaos, on the other hand, is a phenomenon that exists within the existing theories already, whether classical or quantum, and in very general settings. Consider the simple pendulum rod, for example, where we have, see the next equation. There are two general conditions for there to exist solution domains that are chaotic. 1. The system has 3 or more dynamical variables. 2. The equations of motion contain nonlinear coupling terms.
To show that the pendulum rod has chaos, let's shift to first-order equations by change variables and overall normalize such that omega equals 1. See the equation shown. Using omega equals theta dot, not to be confused with the prior omega, we get 3 independent first-order equations. 1. Omega dot equals negative omega divided by q minus sine theta plus alpha times cos phi, where q is the quality factor. 2. Theta dot equals omega. 3. Phi dot equals gamma.
Thus, the simple pendulum rod meets the general conditions, and, indeed, chaos domains are observed to occur. To understand these domains more clearly, it is essential to understand their boundaries, and especially to take note of the distinctive behavior when nearing the boundary of chaos via phenomena involving period doubling. To do this, let's return to the expression for a linear system, derivative of r of t with respect to time equals a of t r of t, and let's assume that with appropriate choice of time it has parameters that are periodic in time. A of t plus t equals a of t for all t. If we consider the propagator through one such period t, we have, with convenient choice for origin of time, the propagator k equals k times t0 equals k of nt, and minus 1 times t. Now consider the propagator for nt steps in time, and using the Chapman-Kolmogorov relation we get, as shown in the next equation. From the above equation we can see that systems with time-dependent parameters that are periodic in time, the propagator k of t0, has the property that it can be determined at certain later times nt, merely by repeated propagations by the period propagator k. Considering that the period propagator is a linear map and area-preserving for Hamiltonian systems, this indicates that much of the future behavior, stable or not, of a periodic parameter system can be determined by the classes of behavior under repeated period propagator mappings. In other words, the behavior of the system is mostly reduced to analysis of the behavior of its period propagation iterated map.
One of the most well-studied iterated maps is the logistic map x sub n plus 1 equals r x sub n times 1 minus x sub n. This map reveals domains for the parameter r where chaos is observed. With r between 0 and 1, the population will eventually die, independent of the initial population. With r between 1 and 2, the population will quickly approach the value r, 1 divided by r, independent of the initial population. With r between 2 and 3, the population will also eventually approach the same value r, 1 divided by r, but first will fluctuate around that value for some time. The rate of convergence is linear, except for r equals 3, when it is dramatically slow. With r between 3 and 1 plus the square root of 6 almost equals 3.44949, the population will approach permanent oscillations between two values. With r between 3.44949 and 3.54409, approximately, from almost all initial conditions the population will approach permanent oscillations among four values. With r increasing beyond 3.54409, from almost all initial conditions the population will approach oscillations among 8 values, then 16, 32, etc. The lengths of the parameter intervals that yield oscillations of a given length decrease rapidly. The ratio between the lengths of two successive bifurcation intervals approaches the Feigenbaum constant delta is almost equal to 4.66920. This behavior is an example of a period doubling cascade. At r is almost equal to 3.56995 is the onset of chaos, at the end of the period doubling cascade. From almost all initial conditions, we no longer see oscillations of finite period. Slight variations in the initial population yield dramatically different results over time, a prime characteristic of chaos. Most values of r beyond 3.56995 exhibit chaotic behavior, But there are still certain isolated ranges of R that show non-chaotic behavior. These are sometimes called islands of stability. For instance, beginning at 1 plus the square root of 8, approximately 3.82843, there is a range of parameters R that show oscillation among 3 values, and for slightly higher values of R oscillation among 6 values, then 12, etc.
If the first bifurcation occurs for mu equals mu sub 1, and the second for mu equals mu sub 2, then it is possible to define a universal constant f after Feigenbaum. See the next equation, where, remarkably, this is a universal behavior for all maps with quadratic maximum. So, in other words, for a simple real quadratic map or complex quadratic map, generator of Mandelbrot set, we arrive at precisely the same constant from their bifurcation maps based on the parameterization of their bifurcation events. Similarly, for the complex quadratic map, the actual asymptote for the C value at the edge of chaos is referred to as C sub infinity and has the value C sub infinity equals negative 1.401155189 . The constant, the absolute value of C sub infinity equals 1.401155189 . Is also known as Myrberg's constant. The Myrberg constant, simply called C sub infinity here, will play an important role in emanator theory, Book 7.